Welcome back from spring break, and we have to get back into chemistry now, so hopefully you didn't miss me or chemistry too much during the break, but we're back now. Before we start, we have a couple of announcements in here about various combinations of Greek letters and their respective pre-health organizations, so Alpha, Aida, Alpha, tomorrow at 6:30, and Delta, Omega, Chi, who is just scrap the Greek letters off altogether, but they're going by DOC now, and that's going to be the 20th, Wednesday at 5:30. A couple other announcements coming Wednesday. All right, so where we are in the course, if you've lost track of time completely in the last week or so, we are getting towards the end of the Chapter 6 material, which is going to be the last section that we'll need for the second midterm. The second midterm, as you'll recall, starts a week from today. Most of you, I think, already signed up for a time because I saw that the CASA time list was pretty well populated. But if you haven't signed up for a time for the exam, try to do that ASAP because I think it's mostly just Monday times that are left now. And also with on that topic, we're going to be having an exam review session as we normally will before an exam. So the problems that we'll go over are already posted in Blackboard, and we're going to go over them in the review session Friday in this room at 1 p.m. And I'll record that and put it on YouTube also, so if you can't come or need to leave early or come late, whatever the case is, you'll be able to see everything that we did. Okay, so that's going to be this Friday at 1 p.m. And then next week I'll have some changes to office hours during the exam, but I'll let you know what those are, and I should be around most of the time. Just a few other things that came up to get in the way of the normal office hour schedule. All right, so with that, we're going to get into the last sort of category of chemical reactions we're going to cover today, which is redox reactions. We've talked about two others, so we'll quickly recap two of those just with a couple example problems to reorient us in what we've been doing recently. So we talked last time about two categories of reactions in aqueous solution, acid-base reactions and precipitation. They have some similarities. They essentially involve exchanging ions between different substances. And so with precipitation reactions, it's going to be two ionic compounds reacting with each other. And so we would ask you on homework questions and test questions that you'll see this week and next week how to balance those equations, how to predict products, and things of that sort, as well as what we'll get to on Wednesday is some stoichiometry dealing with those types of chemical reactions in solution. So in this one here, we're asking you for the balanced equation for the reaction of sodium phosphate and calcium chloride in aqueous solution, and we have to determine what, if anything, will precipitate. So there's a few layers to this onion, and the first one is to remember how to do formulas for ionic compounds. So we have sodium phosphate, so we have to remember the charges of the ions. So if we go to the periodic table, sodium is a monoatomic metallic element, so we can figure out what its charge would be from the periodic table. And so sodium, as we've seen many times now, is in group 1, so it's going to be a +1 cation. Do I not have the laser pointer anymore? Hang on one second. I think I had to restart my tablet. All right, we're back. Sorry, now we have a laser pointer, or what looks like laser pointer, so you can see what I'm pointing at. So sodium is over here in group 1 of the periodic table, so we know it makes a +1 cation. Phosphate is a polyatomic anion, so phosphate is PO4 3-. We have to remember for this section names and charges of ions. We saw that also on the first test, but it's going to come back here. So we have sodium phosphate, which means the formula for the first reactant is going to be Na3PO4. We need 3 sodiums to balance the 3- charge from phosphate. And then we have calcium chloride. So for both of those, we're going to predict the charges from the periodic table. Calcium is a group 2 element, so it's a +2 cation. Chlorine is here in group 7, so it would make a -1 chloride anion. So it's going to be calcium 2+ and Cl-, which means the formula for that ionic compound would be CaCl2. So those are going to be the formulas of both of our reactants. Again, we have to be able to do that, name the formula quite often in this. So we're going to have aqueous sodium phosphate. The two reactions are always going to be aqueous. They're dissolved in solution. And then we have to predict what products that forms. And so remember, when we have two ionic compounds reacting with each other in a precipitation reaction, we just exchange the ions. So the cation from the first pairs with the anion from the second. So our sodium Na plus is going to pair with Cl minus, so we're going to do this pairing for one of our products. And then our second pairing is going to be the cation from the second reactant, calcium, with the anion from the first, phosphate. So we have to balance the charges there. That's a little bit more difficult, but it's going to be Ca3PO4 taken twice. Now we have to think about solubility rules to figure out which, if any, of these products is going to precipitate. So the one that's a dead giveaway is the first one, sodium. Anything that has sodium in it, or any of those group 1 cations, lithium, sodium, potassium, rubidium, cesium, all of those group 1 cations are going to be soluble no matter what they're paired with. So this is going to remain aqueous. So that's not going to be our precipitate. And then if we go to calcium phosphate here, phosphates are almost always insoluble unless they're paired with one of those special cations, lithium, sodium, potassium, and so on. So this one is going to be insoluble because the cation in this case is calcium. It's not from one of the group 1 elements. So that's going to be our precipitate. So part of the question is to identify what will precipitate. So it's going to be calcium phosphate. We have to add some coefficients, though, to correctly balance this. So when we're balancing precipitation reactions and to some extent acid-base reactions, it's helpful to just sort of think of ions sort of as individual units or pieces, because we're not going to be changing the structures of ions. So if we have phosphate PO4 3 minus over here, it's going to stay as phosphate in the product side. So all of our ions, we kind of think of them as when we're balancing. So we have 3 sodiums over here, so we get a 3 over there. We have 3 calciums here. So I think I jumped the gun here. So we get 3 there, but then now that means 2 phosphates, so this is going to become 2, and that has to become 6. A little bit of trial and error there, but we just want to make sure that the ions all balance each other. And so what we see is that we have 2 times 3, which is 6 for sodium, 6 sodiums here. We have 2 phosphates. This 2 modifies the whole phosphate, so there's 2 phosphates, and then there's a 2 there saying that we still have 2 phosphates. 3 calciums, calcium 3. 3 times 2 is 6 chlorides, 6 Cl there. So we can check that a couple different ways, approach it a couple different ways. Coefficients for precipitation reactions typically don't get much more complicated than this, so 6 is pretty large for a precipitation reaction, but that's about as high as they'll get. And that's going to be the balanced form of this equation. So any questions on precipitation real quick before I move on? Okay, so the next major type of reaction we talked about was acid-base reactions. So acid-base reactions have some similarity to what we just talked about with precipitation, where we're exchanging ions. But in this case, it's not really ionic compounds that we're involving. It's an acid and a base. The base is usually an ionic compound, but the acid is going to be a covalent compound. And basically what we're doing is taking the H plus from the acid, the OH minus from the base, and combining those to make water. And then we have some cations and anions left over that form an ionic compound. So here we have sulfuric acid and lithium hydroxide. So sulfuric acid comes from sulfate, which is SO4 2-. So the acid form of that, remember, acids are just going to take the anion and balance the charge with H+. So it's going to become H2SO4 is the acid, sulfuric acid. Lithium hydroxide, lithium is a group 1 element on the periodic table, and hydroxide is OH-. So the formula for lithium hydroxide is LiOH. Just about every base we'll talk about has this general formula, metal with hydroxide. So that's our acid and base, and then we form 2 products. And it wants to know how many moles of water are formed, so we told you here directly that water is one of the products, but anytime you have an acid-base reaction, you're going to form water as a product. So the OH- from the base combines with the H+ from the acid to make water, which is H2O, of course. And then what's left over is going to be the ions. So we have the lithium plus from our base, we have SO4 2- from the acid, and so that's going to make Li2SO4. This could precipitate if it's not soluble, but lithium compounds are always soluble because that's a group 1 cation, so that's going to stay aqueous. And this we'll write as a liquid because it's now actual liquid water that forms. Okay, so that's going to be the reactants and products. We should balance this correctly. So the way to balance acid-base reactions, the way that at least I like to do it, is remember that we have to have 1 H+ reacting with every 1 OH-. So our acid has 2 H+, that means we have to have 2 OH-, which means we need a coefficient in front of there to make sure we have 2 OH- reacting with our 2 H+. If we have 2 of each, that means we form 2 waters. And then I don't think we have to add a coefficient to our last compound here because that has 2 lithiums already. and 1 sulfate, so everything stays balanced with no coefficient on the last one. So that's our balanced one, and we're going to form 2 moles of water in this acid-base reaction because we have 2 H pluses in our acid and 2 OH minuses from the base. All right, questions on acid-base chemistry? All right, so those are 2 of the 3 major categories of aqueous chemical reaction, and those are 2 where, again, we'd have to, we expect you to be able to predict the products of the reactions, and in some cases tell us what is not soluble, and so on. So just like we did for these 2. The last category, we're not going to have you predict reactants and products, but we are going to ask you to balance these and know some of the key terminology associated with them. So the last major category of chemical reaction, there's actually only 3 in the whole world. These are not just 3 of many. These are really the only 3. Acid-base precipitation and redox reaction is the last one. All right, so redox is a term that's sort of a shortened compound adjective, meaning reduction oxidation. And so that redox reactions are going to always involve both reduction and oxidation. So we need the definitions of these. So oxidation is when something loses electrons. Reduction is when something gains electrons. And it may not have been obvious because we weren't really talking about it or thinking about it, but in the previous 2 categories of reactions, precipitation reactions and acid-base reactions, we don't have anything losing or gaining electrons. So if you think about the charges of all the ions that we had involved in those reactions, they don't change between reactants and products, so we're not gaining or losing electrons. If you had sodium plus on the reactant side, it stayed as sodium plus on the product side. If you had sulfate SO4 2 minus on the reactant side, it stayed sulfate on the product side, so we're not gaining or losing electrons in those reactions, but in redox reactions we are. And so that's going to be the combination of these 2 is called a redox reaction. So it's a reaction that involves electron transfer. All right, and as I said, you cannot have one without the other. So you can't have an oxidation reaction. You can't have a reduction reaction. You always have the 2 together as a redox reaction. And something that will also become important when we start balancing these is that you cannot create or destroy electrons. So you're transferring electrons. One of the reactants is losing electrons. One of the reactants is gaining electrons. But the amount of electrons that are lost by one reactant has to equal the amount that are gained by the other. And we use coefficients to help us keep those balanced. So you're never going to lose or gain electrons in net. You're going to just transfer them between 2 reactants and then form products as a result of that. All right, so that's what we mean by a redox reaction. There's a nice mnemonic device for remembering this. So the Latin word for lion is Leo. So Leo here is a lion. And so if you lose electrons, that's oxidation, LEO. Right, so Leo there, LEO. And what do lions say? We learned this in preschool probably. Lions say grr. Right? So if you gain electrons, that's reduction. And hopefully you'll never forget that now. All right, so that's how we remember which one is which. Lose electrons, oxidation. Gain electrons, reduction. And we have to be able to classify that because in many of the situations where we're balancing equations or just asking you questions about them, we need to identify which species is gaining and losing electrons, which one is undergoing oxidation and reduction, and so on. So those are the key terms. And then how do we decide, though, if something is gaining or losing electrons? How do we figure that out by looking at the reactants and products, whether oxidation and reduction is happening or which species is getting oxidized and which species is getting reduced, and so on? We have to use what are called oxidation numbers. And so this is a way of sort of classifying what's called the oxidation state of an element using an oxidation number, and then if that oxidation number changes throughout the chemical reaction between reactants and products, we know that that is a redox reaction, and we can figure out whether that specific reactant is getting oxidized or reduced. We have a few rules we have to learn for assigning oxidation numbers in chemical species. So this is kind of like formal charge. We learned about rules for formal charges, and this is not the same thing, but it's a similar sort of formalism that we follow for oxidation and reduction, which is the difference, though, is if you remember in formal charges, we were assuming that the covalent bonds that we had, basically the electrons were being shared equally between the 2 elements, and we were dividing them up that way. in assigning oxidation numbers, the assumption we make, although I don't usually have to think about this in these terms, but the assumption we make for oxidation numbers is that the electrons are going to go all the way to the more electronegative element. So even if we have a covalent bond between two different elements, we give all the electrons to the more electronegative one and then figure out what would its charge be if it took all those electrons. So it's more of an ionic formalism than a covalent one for oxidation number. Now, the reason we can't just use formal charge for this is because formal charge doesn't tell us whether or not something is being oxidized or reduced. So as an example, if we take NO3 minus nitrate, which was one of the first Lewis structures we did, we saw that one of the oxygens has a -1 formal charge. If we add a proton to that H plus to make nitric acid HNO3, the formal charge of that oxygen goes from -1 to 0, but it's not gaining or losing electrons. So formal charge does not tell us anything about redox. We have to go to this separate convention, which is called oxidation numbers, and we have to learn how to do that. All right, so the strategy here is, again, we're giving the electrons to the more electronegative element. That leads then to a series of rules that we can think about. So the first rule that kind of governs all of them is that the sum of the oxidation numbers will still equal the total charge. So we saw that was also true for formal charges. So if we do this correctly and we have oxidation numbers, we're going to assign oxidation numbers for every element in a compound. So each individual atom or element in that compound is going to have an oxidation number associated with it, and the sum of those will equal the total charge of that compound or ion if it's a polyatomic ion. So the sum of the oxidation numbers will equal the total charge. So that's kind of the overarching rule to keep in mind when we're doing this. Because there's going to be some elements, as we'll see, where the oxidation number is very predictable from the periodic table or just because of its electronegativity. And there's going to be other elements which are more variable, and we have to use this rule to sort of figure those out at the end. All right, so the easiest one to look for is if you have an atom and a neutral element. So some of these are going to be just atoms by themselves, like Na, sodium metal, or Fe, iron metal, or if it's part of a polyatomic element like N2O2, F2Cl2, P4, whatever. If it's an atom and a neutral element, just by itself, the oxidation number will be equal to 0. All right, and that's the only time you have 0 oxidation numbers is for elements. So only if it's uncharged, only if it's an element by itself, will you have an oxidation number of 0. So like I said, all of the standard states of the elements would have oxidation number of 0 for all of the atoms in that, if it's a polyatomic ion, polyatomic molecule, or just that atom by itself. This is also helpful because if we're asking you to identify a redox reaction, if you see an element as a reactant or a product in a reaction, it has to be a redox reaction, because this is the only time the oxidation number is 0. So if it's undergoing a chemical reaction, it's going to change to something else on the other side of the arrow. That means the oxidation number must be changed. That means it must be a redox reaction. So we'll get into that in more detail later on, but the way we identify redox reactions is that oxidation numbers change between the reactants and the product side. And if you have an element, it has to change because it's only 0 when it's an element by itself. And if it changes anything else, the oxidation number will change. All right, and then another one is that, another easy one that we'll see a lot is that if you have a monoatomic ion, so this is an ion by itself, we'll see these a lot. We write redox reactions a lot as ionic equations, so you're very often going to have like a metal by itself, like Na plus or manganese Mn2 plus or something like that. If it's by itself and it has a charge associated with it, the oxidation number is just equal to the charge. And so we don't have to even think about it any beyond that. All right, so anytime you have an ion by itself, or as we'll see in the next rule, if you extend that to an ionic compound, an ion in an ionic compound, the oxidation number is just the charge of that ion. Okay, so that's fairly simple to deal with for ions by themselves or ions that are part of ionic compounds. So we'll say it here. If you have a metal in an ionic compound, as we know, metals form cations when they're involved with ionic compounds. So you're going to have a positive oxidation number. On is the abbreviation for oxidation number, if that wasn't obvious. And it's going to, again, equal the charge of that metal. If your ionic compound has monoatomic anions, like Cl minus, S2 minus, those oxidation numbers would also be the charge. But if it has a polyatomic ion, it's a little more complicated, so we'll deal with those later. But if you have the metal in the ionic compound, it's positive oxidation number equal to the charge. And then from here, most of the other elements have pretty variable oxidation numbers that are not as always going to be straightforward to determine, but there's a few that are generally going to follow a rule. We want to look for those first. So one that we'll see all the time in redox equations is hydrogen. All right. So if you have hydrogen, there's really only three possibilities for the oxidation number. If it's hydrogen by itself, H2, it's going to be 0 because of rule number 2. But if it's hydrogen in a compound, it only has two possible oxidation numbers. So it's going to be +1 when it's bonded to a nonmetal. And this is the most common situation, hydrogen bonded to a nonmetal, like in water or acids and things like that. There are rarer cases where hydrogen is -1. This will be true when it's bonded to a metal. We haven't really seen compounds like this, but they will come up occasionally. So hydrogen bonded to a metal, or a couple of the metalloids as well. We'll see hydrogen bonded to those. So if you have boron and silicon, those are two metalloids. When hydrogen is bonded to those, it's -1. Again, that's because of electronegativity. Hydrogen is less electronegative than most of the nonmetals, but it's more electronegative than the metals and the metalloids, so that's why it's +1, -1 difference there. But mostly +1 for hydrogen, so look for that one as one of the first ones to assign. It's almost always going to be +1. If we go to other elements that are pretty obvious, look for fluorine as well. If you see fluorine in the equation or in the formula for the compound, it's going to be -1 whenever you have fluorine in a compound. And that's, again, because oxidation number is determined by electronegativity. Fluorine is the most electronegative atom on the periodic table. So if we're going to give it all of the electrons in a covalent bond, it's going to complete an octet of electrons. It has one extra electron, 8 versus 7, which is the number of valence electrons that fluorine has. So it'll be -1. And there's nothing that's more electronegative than fluorine. So unless it's F2 element by itself, it's going to be -1 anytime fluorine is involved in a compound, whether it be covalent or ionic. All right, oxygen is another one where the oxidation number is almost always going to be one single value, which is -2. So if we see oxygen, we should think automatically -2. There's a couple of rare exceptions to that. Bonded to itself or to fluorine. So again, it's based on electronegativity. So probably the only two we'll ever see are, if you have H2O2, the oxidation number for oxygen is -1. Because you have 2 +1s from the hydrogen, 2 -1s from the oxygen to balance out to 0. And then if you have a rare compound, but one that you might see, F2O, the oxidation number for oxygen is +2 because we have 2 -1 fluorines. Those are always going to be -1, which means oxygen must be +2 for those to sum up to 0. So very rare cases where oxygen is not -2. If it's an element, it's 0. If it's in a compound, it's almost always going to be -2. And then finally, the last ones that we'll see a lot of, the other halogen elements, chlorine, bromine, and iodine, usually -1 unless they're the central atom. So we see a lot of ions, especially like perchlorate and things like that, where the halogen's at the center. In that case, it's likely not going to be -1. So except when it's the central atom or if it's bonded again to oxygen or fluorine. All right, so those are, it seems like a lot of rules again, but it's one of those things where you do it over and over again until it becomes pretty mindless to be able to do this, to assign oxidation numbers. So there are going to be potentially problems on the homework assignment and test where that's exactly what we have to do. So let's just practice these rules and put them into good use. So we would give you an example. We say determine the oxidation number of each element in sodium sulfide. And so again, we're dealing with compounds here very often, and we can assign an oxidation number for every element in the compound. Every atom in the formula can get its own oxidation number. So if we have sodium sulfide, as we saw before, sodium is Na+, sulfide from the periodic table is S2-. So the formula for this is just Na2S. And if we want to assign oxidation numbers for ionic compounds, it's very simple. So this time we just need to know the charges of the ions. We've already learned how to do that a long time ago. So we see that sodium is a +1 ion, so the oxidation number would also be +1. Sulfur as a monoatomic ion is -2, so it's going to have a -2 oxidation number. And so those would be the two oxidation numbers for sodium sulfide. Sodium +1, sulfur -2. So anytime you have an ionic compound, especially a binary ionic compound that just has two different ions in it, two monoatomic ions, you can just use the charges to find oxidation number. That's all you have to do. We can verify that the sum equals the overall charge. So remember that the sum of the oxidation numbers needs to equal the overall charge. Sodium sulfide is a neutral compound. So if we have two sodiums that are +1, I didn't write that very well, +1 for sodium. And then we have one sulfide, which is -2. The sum of those equals 0. So same story for ionic compounds. It's based on the charge. The sum of the charges equals 0. Sum of the oxidation numbers equals 0 as well. Now that's a relatively simple example because for ionic compounds like that, we don't have to really learn any new rules. But let's see what happens when we get to something that has a covalent compound with a few more elements in it. So here we want to determine the oxidation number for each element in phosphoric acid. So again, the first thing to do is figure out the formula. So phosphoric acid comes from phosphate. Phosphate is PO4 3-. We saw that one I think a little bit earlier as well. And so that means the formula of the acid, we're going to add hydrogen to balance this charge, so it becomes H3PO4. Okay? So in this case we have hydrogen, phosphorus, and oxygen. And the way we typically do this is we look first for the obvious ones. So hydrogen and oxygen are going to be the two that we're going to zone in on first because their oxidation numbers are almost always the same. So for hydrogen, anytime it's in a covalent compound with no metals in it, this compound doesn't have any metal in it, so hydrogen will be +1 in that situation. Okay? So we have +1 for hydrogen, and that's going to be true anytime hydrogen is part of a covalent compound bonded with other nonmetal elements. Oxygen is going to be -2 unless it's bonded to itself, so unless it's in hydrogen peroxide, H2O2, or bonded with fluorine, which is not, so we can assign oxygen as -2. Again, except for the very rare cases like H2O2 where oxygen is bonded to itself, probably the only one you'll see where that's the case, we're going to have oxygen assigned as -2 whenever it's in a compound. And that leaves phosphorus, which is variable. So these group 5 elements, nitrogen, phosphorus, they can have a few different oxidation numbers, so we can't easily assign it. So then we have to use the rule now that the sum of all the oxidation numbers has to equal the overall charge of the compound. We have oxidation numbers for 2 of the elements. We need to find the third one using that rule. So the charge of this compound, phosphoric acid, is 0. It's a neutral covalent compound. And that's going to be equal to the sum of the oxidation numbers. So our formula has 3 hydrogens, and each one has an oxidation number of +1 as we saw. So when we're summing oxidation numbers, we have to do it for each individual atom in the formula. So if we have 3 hydrogens, they're each going to have a +1. We saw that we have oxygen is -2. We have 4 of them in the formula. So each oxygen is going to be -2. So we have 4 -2s from oxygen. And then we have 1 phosphorus, which we don't know the oxidation number of yet. So it just becomes a little bit of algebra. What do we have to add? +3 minus 8 is -5. What do we have to add to that to get 0? So this is our unknown. We move everything over and we get that the oxidation number for phosphorus is +5. So this is a +5. We add that to +3. We add it to -8. The sum is equal to 0. All right, so that one is our variable one. We find that last. We get +5 for phosphorus, and those would be the 3 oxidation numbers in phosphoric acid. All right, we do hydrogen, oxygen first, phosphorus last to make sure that the sum of the oxidation numbers equals the overall charge, which is 0 for any sort of neutral compound. All right, questions on that? All right, last one of these we'll go through, I believe. Yes. The last one we'll go through is the oxidation number of each element in sulfate. So sometimes we're going to have to deal with ions by themselves, not part of a neutral acid or ionic compound. And so in that case, we have to just, again, think about the different rules that we learned. So SO4 2- is our ion sulfate. Now we have to find the oxidation numbers for each element here, which is going to be sulfur and oxygen. All right, so we do the obvious one first. Again, oxygen is not bonded to itself here. It's part of a covalent compound. The structure is given here just as a little aside, so we see that there's no oxygen-oxygen bonds. So that means that oxygen is going to be -2. Anytime you see oxygen in a compound, it's going to be -2 unless it's bonded to itself or fluorine. So we assign oxygen as -2. Then we have to find sulfur, which again can be variable. And we're going to use the rule that the sum of the oxidation numbers has to equal the overall charge. The only difference here is that our overall charge is not 0 anymore. It's -2 for sulfate. So -2 is our total charge. And that's going to be equal to the sum of all of the oxidation numbers. So we have 1 sulfur in the formula, which we're trying to figure out what the sum of that is. And then we have 4 oxygens in the formula, SO4, 2 minus, each is -2. So what do we have to add to, this is oxygen, this is sulfur, what do we have to add to -8 to get -2? We can do algebra. +6, I heard it, good. All right, so that means our sulfur oxidation number is +6. All right, so we get +6, we get 4 -2s. The sum of 6 and 4 -2s is -2, which is the overall charge. All right, so that's the process we're going to follow for determining oxidation numbers. One other thing about oxidation number that is sometimes helpful, it's not really going to be a rule that you use all the time, but at least it's a good way of checking yourself, is that for the main group elements, I guess probably any element, but especially the main group elements which have these A numbers by them, so group 1, group 2, 3, 4, 5, 6, 7, 8, the maximum oxidation number is equal to the group number. So we saw that in that compound sulfate, the oxidation number for sulfur was +6. Sulfur is in group 6, so that's the highest oxidation number it could ever have. Okay, so if you ever get an oxidation number that's larger than the group number, more positive than the group number, you know you must have messed something up. So sulfur can never be above +6, the halogens can never be above +7, and so on. So that's a helpful way to check yourself sometimes if you're getting these relatively large oxidation numbers like +6 for sulfur. That's okay though, because sulfur is in group 6, so it can be that high if it needs to be. All right, questions on oxidation numbers. Now the more important thing we're going to have to be able to do is use these to balance redox equations. And this is a process sometimes that we're going to learn how to do. But let's start again by giving some more terminology before we get into the balancing part. All right, so we have what are called oxidizing agent and reducing agent. So very often we're going to give you an equation that could be a redox equation and ask you to identify what is the oxidizing agent, what is the reducing agent. The terminology is a little bit confusing here at first glance because the oxidizing agent is the reactant that gets reduced. Okay? So the reactant that gets reduced is called the oxidizing agent. All right, and another little point about the terminology is that, first of all, oxidizing agent, reducing agents are always going to be reactants, so you never have to look on the product side to try to find what those are. It's always a reactant. It's the oxidizing agent. Another reactant is reducing agent. And then the other thing is that the oxidizing agent will be the entire reactant. So as we saw, we assign oxidation numbers for every element, but then the oxidizing agent is the whole compound that that element is part of. So let's say if we had, in this previous example, let's say we found that sulfate was our oxidizing agent with sulfur having its oxidation number change. The whole thing, sulfate, would be the oxidizing agent, even though the oxidation number of only one of the elements is likely going to be changing. So it's the whole reactant that element is part of is going to be classified as the oxidizing agent. Now, why do we call it the oxidizing agent if it's getting reduced? Remember what an agent means. So if you're an agent of change, you're the person that's causing the change, not the person that is being changed. So it's an oxidizing agent is the one that does the oxidizing. So it is causing something else to get oxidized because we can't have reduction without oxidation. So that's why we call it the oxidizing agent, even though it itself is getting reduced because it's causing something else to get oxidized. And the way that we identify it in a chemical reaction is, again, we're going to assign oxidation numbers for all the reactants and products. And the one that's going to be the oxidizing agent, or the one that gets reduced, is the one where the oxidation number decreases during the chemical reaction. All right, so if the oxidation number starts out at a bigger, more positive number and ends up at a smaller or more negative number, that means it's getting reduced, and that would make it the oxidizing agent. Again, it's always the difference in oxidation number that tells us that, the difference between the reactant and the product side. Okay, so that's how we identify oxidizing agent. And then reducing agent is the exact opposite. It's another reactant, and it's the one that gets oxidized. Reactant that. And just like before, we call it the reducing agent because it's the one that does the reducing or causes something else to get reduced. So that's the reducing agent, and the oxidation number will increase during the reaction. So the oxidation number on the reactant side will be smaller than on the product side for whatever is part of the reducing agent. And as I said, and we'll see some examples of, it's typically only one element in that whole reactant that's going to have its oxidation number increasing or decreasing. But even if this one element is having its oxidation number changing, that makes that whole reactant the oxidizing or reducing agent as it is. Okay? So that's the terminology. Let's see it in action now with a couple examples. So I'm going to give you two chemical equations here and ask you first, is this or is this not a redox reaction? And then, if so, what is the oxidizing agent? Okay? So we have to first assign all the oxidation numbers. So if we're asked to identify something as potentially a redox equation, we have to assign oxidation numbers in all the reactants and products and see if they are or are not changing. Okay? So if we go to PCl3, remember we don't worry about coefficients, we just look at the formula of the compound itself. So we're going to assign oxidation numbers for every element in all three of these formulas here, reactants and products. So as we said, chlorine in covalent compounds is typically -1 unless it's the central atom. So we're going to have -1 for chlorine. We have 3 -1s for chlorine. So what does phosphorus have to be to balance that out to 0? +3. So we want the sum of these to be 0. So we have +3 for phosphorus, 3 -1s for chlorine. So the sum is 0. Oxygen is an element by itself. So what's the oxidation number? All right, it's going to be 0 if it's by itself. Any element by itself with no charge. So even though it's bonded to another oxygen, it's still uncharged, not with any other element, so it's going to be 0. So any elemental form of any element, whether it's monoatomic, diatomic, whatever, is going to be 0 oxidation number. And this, as I said, is a shortcut that allows us to identify that this will be a redox equation. Even if we see an element in there, it must be a redox reaction. But let's finish out and figure out all the oxidation numbers. We'll need those anyway. So for POCl3, we still have 3 chlorines that are -1 because they're part of a covalent compound. Oxygen is going to be -2 as it typically is in compounds. Remember, when oxygen is part of a covalent compound, it's -2. So if we have 3 -1s and 1 -2, what do we need for phosphorus now to balance to 0? +3 would give us still a negative. So it's -3 -2 is -5. So we need a +5 on phosphorus to make the whole sum equal to 0 because this is a neutral compound. All right, so our sum of our oxidation numbers is going to be 0 for that if we have a +5 on phosphorus, -2 and -1 for those. So if we look at this, we have to identify is this a redox reaction, and if that's going to be true, we need to have oxidation numbers that are changing. And what we see is that phosphorus goes from +3 to +5, so that one is changing between reactants and products. And we see that oxygen on the reactant side is 0, and it's changing to -2 on the product side. So we have changing oxidation numbers, and so that means, yes, it is a redox equation. Okay? So anytime oxidation numbers are changing, it will be a redox equation. If you had any other type of chemical reaction, acid-base precipitation, you would have no oxidation numbers different between the reactants and product side. All right, so that is a redox reaction. Now we have to identify the oxidizing agent. So remember, the oxidizing agent is the one that gets reduced, which in terms of oxidation number means that its oxidation number is going to decrease during the chemical reaction. So we see that O2 goes from 0 to -2. The oxidation number of oxygen is getting smaller between reactants and products. So this is going to be our oxidizing agent. And PCl3, so that means O2 is the oxidizing agent because that's the one that gets smaller. And then remember, it's the whole species that's going to be involved as the oxidizing or reducing agent. So phosphorus is the element that has its oxidation number increasing from +3 to +5. This doesn't ask us to identify the reducing agent, but if we wanted to, we would see that phosphorus's oxidation number is increasing, so that means phosphorus is going to be part of the reducing agent. So that means the whole thing, PCl3, is the reducing agent. All right, that wasn't part of this question, but we can identify that. And as I said, you cannot have one without the other. So if you have an oxidizing agent, you also have to have a reducing agent. If one element has its oxidation number increasing, there must be another element somewhere that has oxidation number decreasing. You can't have one without the other. All right, so any questions on this one? Yep. So oxygen is an element. It's O2, has no other elements in the formula, has no charge associated with it, so the oxidation number will be 0. Is that what you're asking about, how to assign the oxidation number? It's not -2 because it's not in a covalent compound with other elements. So oxygen will be -2 if it's with other things. So here it's with phosphorus and chlorine in a covalent compound. But if it's an element by itself, just O2, it would be 0. And that's true of any element by itself. Now again, some of the elements are polyatomic, so like O2, N2, P4, S8. But if it's just one element in the formula and there's no charge, it has to be 0 for the oxidation number. Okay? Any other questions? Okay. All right, let's do one other. It looks fairly similar. So now we're going to take our POCl3, which is the product of the last reaction, phosphorus oxychloride as it's commonly called, and we're going to react that with water to make phosphoric acid and hydrochloric acid. And we want to know, is this a redox reaction? Now, very often for redox reactions, it's not easy to tell just by looking. This one doesn't have any elements involved, so we can't really easily tell just by looking at it that it is or is not a redox equation. So we have to go through again and assign oxidation numbers to figure this out. All right, so in this equation here, we start with POCl3, which we saw was the product of our last reaction, so we already assigned oxidation numbers for that one. We saw that there was 3 -1s for chlorine, -2 for oxygen because it's part of a covalent compound, and that left +5 for phosphorus. So that's the same one we just did. We have some other ones out here. So we see water H2O. This is going to show up all the time in chemical equations that we deal with, and especially redox equations, so we should get used to assigning the oxidation numbers of this super fast. Oxygen -2, hydrogen +1. Remember, if hydrogen is in a covalent compound, it must be +1. Oxygen in a covalent compound with rare exceptions is -2, so that's what we're going to see for water all the time. We go to H3PO4. We just did this one as an example by itself, phosphoric acid. Oxygen in a compound is -2, hydrogen in a compound is +3, and that left +5 for phosphorus to balance those out to add up to 0. And then for HCl, diatomic molecule, covalent compound, +1 for hydrogen. Chlorine must be -1 so that they add up to 0. Okay? So those are all the oxidation numbers, and if we look at each individual element that's involved, phosphorus, oxygen, chlorine, and hydrogen, we see that on the reactant side, phosphorus has an oxidation number of +5. On the product side, it is also +5. Okay, so that one's not changing its oxidation number. Oxygen, we have -2 here, -2 from water, so -2 in both of the reactants. And then on the product side, oxygen is also -2 phosphoric acid. All right, chlorine, we have -1 on the reactant side. On the product side, still -1. And then hydrogen, we have +1 on the reactant side and still +1 both places. Sorry, I wrote that as +3. That should be +1. You guys need to yell at me if I make a mistake. All right, so hydrogen is +1 each. There's 3 +1s, so that's +3 total, but each one is +1. So sorry about that. But anyway, if we look at those closely, we see that we have +1 here for water, and then in both products we have hydrogen, which is still +1. Okay? All right, so we see that all of the elements in this chemical equation have the same oxidation number on the reactants and product side, so that would mean this is not a redox reaction. Now, it's not easy to identify this as such because it's not a conventional one that we're used to, but this, as it turns out, is an acid-base reaction. We would not ask you to tell us that it's an acid-base reaction because it's not the standard form that we're used to and that we expect you to know, but this is an acid-base reaction. We just know from this that it's not a redox reaction because none of the oxidation numbers are changing. All right, so again, it's not always obvious from the reactions from products that that's the case, but if we assign all the oxidation numbers and none of them are changing, we know that it's not going to be a redox reaction. All right, questions on that one? All right, the last thing we're going to cover today, which is going to be sort of the big topic for this chapter, you're going to have, I'll tell you right off the bat, 2 problems on the test that are going to ask you to do this, which is balancing redox reactions. The gentleman that puts together the test question banks loves oxidation redox reactions apparently, because there's always going to be 2 questions on this test about it, and so that's a decent portion of the test this time. So we have to learn how to balance redox equations because a lot of these end up being fairly complicated. We can't just easily do them by inspection. We can't just look at reactants and products and figure out, oh, I have 3 chlorines over here, so I need 3 over there. They end up becoming complicated. And the other factor too is that to balance a redox equation, very often we're doing these in aqueous solution with charged ions as reactants and products. We have to make sure not only do the atoms balance on each side, but the charges balance also. So in many cases, it's not easy to do this just by inspecting reactants and products and trying to make them balance out with each other. So we're going to learn a method for doing this. Now, I think this is fun. You guys probably don't have the same definition of fun as I do in most cases. Your definition of fun is probably more of what you were doing last week. But I think this is a pretty fun part of chemistry and learning how to do this. It's kind of like putting a puzzle together. And there's a series of steps we're going to follow that allow us to do this. It's just one of those things you have to practice over and over again to get good at, just like a lot of things we do in this class. Okay, so we're going to break this down into a few steps here. And so the first thing, just like we've been doing, is you need to assign the oxidation numbers for each atom in the chemical equation. Okay. So this is something that you again need to get good at and be able to do it very quickly, because this is only really a part of what you have to do to balance these. So we're going to assign oxidation numbers for each atom. That will tell us off the bat if it is or is not a redox equation, if that's what we're asking you. But also, when we're balancing redox equations, we need that information to help us, as we'll see. All right, so we have this one here that we're going to work through step by step. We have Cl minus plus MnO4 minus, which is permanganate, plus H plus, making ClO minus, which is hypochlorite, manganese plus 3 cation, and water. So again, a lot of these redox reactions involve charged ions, as aqueous species. I didn't draw the little AQs in here, but these would all be aqueous typically for these types of equations as well. All right, so we're going to assign oxidation numbers for everything. If you have ions by themselves, those are the easy ones because that's just the charge. So if we have a Cl minus, the oxidation number is just -1. So no more thought needed for that one. MnO4 minus is a little bit of a tough one because it has a metal in here, which is variable transition metal specifically. But just like before, we have oxygen involved in a compound, and unless it's H2O2 or OF2, those 2 rare examples where it's not, oxygen is going to be -2 in any sort of compound or ion that it's with. So now we have to figure out what manganese is using that as our starting point. So if we have 4 -2s for oxygen, the overall charge is -1. So what does the oxidation number on manganese have to be? A little bit of algebra. Someone said it. +7, good. Okay, so we have +7 for manganese. So +7, 4 -2s, the sum of those would give us -1, which is the overall charge. So there's going to be some of these in here that are a little bit tougher than others. But a lot of these are simple, like H+. Hydrogen by itself with a +1 charge means it has a +1 oxidation number. Okay. If we go to the product side, we have ClO minus. Oxygen bonded to anything else but itself gives us -2. We have a -2, but the overall charge is -1. So what does that mean? Chlorine has to be +1, right? 1 -2 is -1 for the overall charge. Ion by itself, +3. So we just have to assign the oxidation number as the charge. And then our good friend water, which we're going to see over and over again, +1 -2. After today, you shouldn't have to think about that anymore at all for water. Okay, so those are all the oxidation numbers. We have to assign them first. And then what we're going to do is we're going to determine the number of electrons that are lost and gained from each of the species that are changing their oxidation numbers. So typically in a redox equation, you're not going to have every reactant losing or gaining electrons, just some of them will, usually a pair of them as we saw. So we have to determine the number of electrons lost and gained for each species that changes its oxidation number. All right, so we have to find the ones that are changing. So we see that chlorine here starts as -1 and goes to +1. So I'm not going to write in all the oxidation numbers again, but we'll write the ones that are changing. -1 to +1 for chlorine. And then the other one that's changing is what? Manganese, someone said it, good. So we have +7 for Mn over here and +3 over here. So that one is also changing. So we find the ones that are changing. We zoom in on those to begin with, +7 and +3. And then we have to figure out the number of electrons that are lost and gained from each of those. And that is just going to be given by the difference in oxidation number. So Cl is going from -1 to +1. So what's the difference between the two? That's 2. And it's getting bigger, so that means it's going to be losing 2 electrons. All right, now it doesn't really matter. We don't necessarily have to keep track of if it's gaining or losing necessarily, because we just need the number that's involved, which is 2 electrons. Okay, and it's 2 electrons because the difference is 2. -1 to +1 is a difference of 2. And then for manganese Mn, we go from +7 to +3. The oxidation number is getting smaller, so that means it's gaining electrons. And how many electrons is it gaining to go from +7 to +3? It's just the difference, which is 4. Good. All right, so 4 electrons for manganese. Okay, so that's the first thing we need to do, is identify how many electrons are being transferred or being lost and gained from each species, which is 2 for the chlorine, 4 for manganese. All right, and then what we do in step 3 is we need to add coefficients to make sure that we can balance the number of electrons lost and gained. Because as I said at the outset, we're not going to create or destroy electrons, so the number of electrons that we lose has to be equal to the number of electrons that we gain. All right, so as we saw, chlorine going from Cl- to ClO- is losing 2 electrons. It's a difference of 2 in its oxidation number, as we saw in the last step. And then manganese here, going from MnO4- to Mn3+, we gained 4 electrons. So the number of electrons lost has to be equal to the number of electrons gained. Are they equal right now? So how do we make them equal? We have to double this one, okay? So if we double the number of electrons there, that's going to make it equal to 4. And to do that, we add coefficients in front of both of those. All right, so you always have to add coefficients both on the reactants and the product side to make sure the number of electrons are balanced. So now we have each Cl- is losing 2 electrons, but there's 2 of them participating. So that's going to be a difference of 2 times 2, which is 4. 4 electrons total, 4 electrons being gained here. Now we also, because of that, we want to set these coefficients to 1. So the first thing we're always going to do in redox equations is we're going to set the coefficients for the species that are changing their oxidation number, being oxidized and reduced. So if we make a coefficient of 2 here, that gives us losing 2 electrons but doing it twice. That's going to be a total of 4. This one is gaining 4 electrons, so we just need one of those to gain all 4 electrons, and so we set the coefficients there. These coefficients we don't want to touch anymore for the rest of this process. So once we set the coefficients that are involved in the redox, the ones that are gaining and losing electrons, we don't want to change those at all, because that's going to throw off the number of electrons that are being gained and lost. Last step, though, we sometimes have to do additional steps to balance the rest by inspection. So this is where we just have to look at elements on both sides and make sure that we have the same number of each. Okay? So we've set the coefficients here to 2, 1, 2, and 1. Those ones were determined by the number of electrons lost and gained. The rest of these we just have to look at what's going on here. So typically what we're going to do is we're going to balance water first by looking at the number of oxygen atoms. So here we have 4 oxygens in MnO4-. We have 2 in ClO-. So how many waters do we need to make sure we have 4 on the product side? We need a number 2 there. So now we have a total of 4 oxygens on each side. 4 there, 2 plus 2 for that. If we add 2 waters, that's a total of 4 hydrogens, so we need to have 4 H pluses. So very often you're going to do water and H plus last. Water allows us to make sure that oxygen is balanced, and then after we add water, we can figure out how much H plus we add to the other side to make sure that hydrogen is balanced. All right, so we set these coefficients here, 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 and here using number of electrons. The last 2 coefficients, we just have to make sure that we have the same number of atoms, same number of elements on each side of the arrow, just like we always do for a balanced chemical equation. All right, so that's how we do it, again, step by step. Any questions on those steps in abstract before we do a couple more examples of this process? All right, so let's go through one more and just see it from start to finish. So as I said, typically we're going to give you reactants and products for these. We're not going to expect you to be able to predict what they would be. That's pretty much impossible to do for most redox equations. So we give you reactants and products, and we're going to ask you then to put coefficients in front of them. All right, so the way we do this is we again assign oxidation numbers first. So every single element, most of these are actually going to be easy for us. The only one that's difficult here is Cr2O72-. All right, that's kind of a beast. So we have oxygen is -2 anytime it's in a compound or polyatomic ion. So the overall charge for this is -2. We have 7 -2s for oxygen. We have 2 chromiums, and so what do those have to be to make this? So X is going to be the charge for the oxidation state for chromium, which is going to be +6. It'd be 12 total, but then there's 2 of them, so each one is going to be +6. Remember, we're going to be assigning oxidation numbers for each element. So the total for chromium would be +12, but there's 2 of them in the formula, so each one is +6. Okay. All right, so we have +6 for chromium. That was the difficult one in this case. I- is an ion by itself, so it's just going to be -1. H+ by itself is +1, so we've seen those before. Chromium by itself, +3 with a +3 charge. I2 is an element, no charge, so what's the oxidation number going to be for I2? 0, good. And then we have water, which is going to be our old friend, +1 -2. Okay, so we assign all the oxidation numbers first. Now this problem has a little bit of a twist on it that we didn't see before, and there's a couple of different ways of dealing with this, but I'm going to show you what my method is for dealing with this. So the twist here is that we see that the ones that are changing, we have chromium going from +6 to +3, and then we have iodine going from -1 to 0, so we're going to identify the ones that are changing their oxidation numbers. But we see that we have 2 +6 chromiums, and over here we just have 1 chromium by itself. So we know at the very minimum we're going to need a coefficient of 2 there to make sure that we have the same number of chromiums on each side. So I like to put it in right at the beginning to tell myself that whatever these coefficients end up being, the coefficient on this has to be 2 times the coefficient of this, because those are the only 2 places that Cr appears. So we have to have the coefficient over here has to be twice of whatever it is over here to make sure that we have the same number of chromium atoms on each side. Again, you don't necessarily have to do it that way, but it also I think makes it easier to keep track of number of electrons, as I'll show you here in a second. And similarly for iodine, I- goes to I2. We have 1 iodine by itself over here. We have 2 bonded to each other over here. So at minimum, we're going to need a coefficient of 2 there. Now we're likely going to have to adjust those coefficients beyond this, depending on how many electrons are involved. But I just like to put these 2's in right away to remind myself that this coefficient has to be twice whatever the coefficient is over here. And same with this coefficient being twice whatever this is. Now we can go ahead and count electrons. So we see that chromium is going from +6 to +3. So that's a difference of 3, but that's for each chromium atom, right? So we have 2 chromium +6's going to 2 chromium +3's. So the total is going to be, we have 3 electrons for each one, but it's going to be happening twice, right? There's 2 +6's to 2 +3's, so that's a total of 6 electrons. All right, each one +6 to +3 is 3, but there's 2 chromiums because there's dichromate Cr2O7, so that's going to be a total of 6. And then similarly for the I- one, we have 2 I- going to I2. Each one is going from -1 to 0, so that's 1 electron for each iodine, but it's 2 of them that are happening in this case. So it's going to be 1 electron for each iodine, but it's happening twice. That's going to be a total of 2 electrons. So sometimes we have to do this to be able to count the electrons correctly, because if it's more than one element in the formula that's changing its oxidation number, we have to make sure we account for that. So again, Cr2O72-, there's 2 chromiums. Each is gaining 3 electrons. So it's going to be a total of 6 electrons. And similarly, we have 2 I-, each losing 1 electron. So that's a total of 2 electrons. So make sure we count electrons correctly. That's a little bit of a different story here. And then we have to make sure the number of electrons balance. So we have 6 electrons for the reduction part. We have 2 electrons for oxidation. So what coefficient do we have to add to make those the same? 6 and 2. What do we multiply 2 by to make it 6? 3. Good. So we have 3 there. So we're going to. So what that means is that this coefficient here is going to be multiplied by 3, and same with this coefficient here multiplied by 3. So again, it's the coefficient for both of these, I minus and I2, that have to be multiplied by 3. So what that leads us to then is that Cr2O72 minus is going to still be a coefficient of 1. But then I minus, which we put the 2 in to remind ourselves that there's 2 of those, has to be tripled to make it a total of 6 I minuses. We'll do H plus and water last, as we usually do. And then on the product side, we still have the 2 in front of chromium plus 3 to make sure that chromium stays balanced, but we don't change that coefficient anymore because that's already a 6 electron process. And then for I2, we saw that we had to triple that coefficient to make sure that it's a total of 6 electrons. So it's going to be 3 I2s. And then our last product is water, so we're going to do that last. All right, so then we have to figure out how much water and H plus to add. So we have 7 oxygens on the reactant side from Cr2O7. So that means we have to add 7 waters on the product side to balance out oxygen. 7 waters gives us 14 hydrogens, so we need a 14 H plus. All right, so again, the coefficients are, in some cases, kind of big for these, so it would be a little bit hard to do this by inspection. So the only difference here, the only thing that was a little bit more difficult than the last one was balancing the number of electrons, making sure we account for the fact that there's 2 chromiums that are changing their oxidation number, as well as 2 iodines that are changing their oxidation number, and we have to make sure we count those correctly to add the correct coefficients. All right, questions on this one? All right, a couple other ones, I guess, just to drive this point hard. 2 more, if you can handle it. Just want to make sure I keep track of where we're going. All right, so 2 more oxidation numbers to deal with. 2 more redox reactions, sorry. So we're going to balance the following reaction and determine the sum of the coefficients. So again, a typical Blackboard setup is we would ask you to balance and then ask you to determine, let's say, the sum of all the coefficients, or sum on the reaction side, sum on the product side, and so on. All right, so let's go through this one. This is an ionic compound, so it's going to be KiO4. Anytime we have an ionic compound, potassium is a group 1 element, so it's going to be +1. We have 4 oxygens that are going to be -2. And then to balance the charges, we have 4 minus 2s is -8, +1 is -7, so that means iodine has to be +7 for those to add up to 0. All right, so again, this is an ionic compound, KiO4, which is called periodate, similar to perchlorate. We have NH3, hydrogen is +1 in any covalent compound, and then it's going to be -3 for nitrogen to balance that. 3 + 1 is 1 - 3. Ki, ionic compound, +1 and -1, group 1 and group 7, so nothing difficult there. N2 element by itself is 0, and then Old Faithful water, +1 - 2. All right, so we have to, again, quickly be able to do that to assign oxidation numbers, so take some time learning that part of it that we covered earlier today. We have to figure out which ones are changing. So iodine is going from +7 to -1, and nitrogen is going from -3 to 0. But again, we should remind ourselves that we're going from NH3, which only has 1 nitrogen, to N2, which has 2. So I like to slap a little coefficient of 2 on there from the start, just to remind myself of that. So we have 2 nitrogens going from -3 to 0. So the number of electrons that are involved, then, we have iodine going from +7 to -1. So what's the difference there? 7 to -1 is 8, a difference of 8, right? So 8 electrons. And then we have 2 -3s going to 0. So each one is going to be losing 3 electrons. So we have 3 electrons, but there's 2 of them. So right now, as it's written, that's going to be 6 electrons. 2 - 3 is going to 2 zeros. Right, again, because it's N2, so there's 2 of those in the formula. 8 electrons and 6 electrons. How do we balance these? You have to figure out what's the proper math term. The least common multiple of 8 and 6, I guess, would be the math terminology. So we have to figure out how can we balance those number of electrons with whole numbers. So is there any whole number we can multiply 6 by to make it equal to 8? No, so we have to think about now what's the least common multiple of 6 and 8. So back to like junior high math class. All right, so I think I heard someone mutter it, so I'm going to go with 24, right? So the least common multiple of, I hope that's the right terminology because my math sucks. But anyway, least common multiple of 6 and 8 is 24. So we're going to triple this, multiply it by 3 to make it 24. We're going to quadruple that, multiply it by 4 to make 24. That's the smallest number of electrons that allows both of those to be balanced by just multiplying each by a simple coefficient. Okay? We don't really want to deal with fractional coefficients here. We could, but typically we don't, so we're going to find the smallest whole number that allows us to do this. If we had made it 12 electrons, we'd have to multiply this by 2 and this by 1.5. We'd be dealing with fractions there. So 24 electrons allows us to just use whole numbers now, and there's no smaller whole numbers that will work for that. So that means we're going to triple the coefficients associated with potassium periodate and potassium iodide. We're going to quadruple the coefficients associated with NH3 and N2. So what that leads us to then is a coefficient of 3 there and there. That coefficient is going to be quadrupled to make it 8, and that's going to give us a 4 there. So we're going to have 3 KiO4 plus 8 NH3. So we have to quadruple that coefficient, which was already 2 to begin with. We triple this coefficient to make 3 Ki's. We quadruple the coefficient to make 4 N2s, and then we have water that we still have to balance at the end. All right, so these coefficients are set now, so we don't want to change those anymore because they've already been determined to be the right coefficients to keep the number of electrons balanced. So we just have to figure out what's missing for oxygen. So here we have 12 oxygens. This 3 times 4 is 12. So we have to have 12 waters. And then we can also verify that there's now 24 hydrogens, 12 times 2, 8 times 3, so the balancing works out. So we will give you all the reactants and products you need. You don't want to add any extra ones to here. And so we just need a coefficient of 12 to make sure that we have the same number of oxygen on each side. And then once we do that, we also have the same number of hydrogens, and it all works out. All right, questions on that? All right, last redox equation to balance, which shows us one other trick of the trade that we're going to need to use sometimes. So we have zinc and nitric acid making zinc nitrate, NO, and water. All right, so we're going to assign oxidation numbers first. That's always our first step. All right, so zinc is an element by itself, so that makes it 0. HNO3, we have hydrogen in a covalent compound is +1. Oxygen in a covalent compound is -2. 3 minus 2's, a +1 is -5. That means we need a +5 on nitrogen. All right, so that gives us a sum of 0. And then we have zinc nitrate. This is an ionic compound now. So if we have 2 NO3 minuses, what is the charge of the metal? +2. Okay, so that's the charge in the ionic compound. If it's an ionic compound, the charge of the metal is equal to the oxidation number. So it's +2 for zinc, and then we have NO3 minus. And we just lost the hydrogen from here, so that doesn't change oxidation numbers. So we have 3 minus 2's for oxygen. The sum is going to be -1 for each nitrate. So we can treat these polyatomic ions as individual ions is sometimes helpful. So that's going to be +5. So it's still going to be +5 for nitrogen, still -2 for oxygen. We have NO, which is -2 for oxygen, which leaves +2 for nitrogen to make the sum equal 0. And then we have water +1 and -2. All right, so those are the oxidation numbers. Now what we notice here is that we have zinc going from 0 to +2, so that's one of our oxidation numbers that's changing. And we have nitrogen going from +5 to +2, so that's the other one that's changing. But the problem we also have here is that some of our nitrogen, which is starting out as +5, is still staying as +5 on the product side. So we only have one reactant that has nitrogen in it, which is nitric acid, HNO3. Some of that is going to be forming NO, which has a different oxidation number, but we still need more HNO3 here to keep this nitrate, which is part of the product here, zinc nitrate. So in this situation here, where some of the nitrogen does not change its oxidation number, the way that I like to handle this is to separate it out into two pieces. All right, so we have zinc plus HNO3 going to zinc nitrate, NO, and water. And as we saw, we have our changing oxidation numbers here for zinc to zinc 2+, changing oxidation numbers here for NO3 to NO2, to NO, which is a +5 to +2 change in oxidation number. But we also have some nitrogen that's not going to be changing its oxidation number, so I'll add that in as a separate piece that will balance at the end. Remember, everything that's not changing its oxidation number in the equation, we're going to balance by inspection at the end. So we'll balance Let me move that over a little bit. We'll balance this HNO3 at the very end after we've done the oxidation number approach to get the number of electrons correct. So this one, as we said, is going from 0 to +2, so that's going to be 2 electron process for zinc. This nitrogen is going from +5 to +2, so that's going to be a 3 electron process. And so how do we balance these out? If we have a 2 and a 3, how do we make them the same? Least common multiple of 2 and 3 is 6, so we're going to triple that, and we're going to double that. So then what we get is this coefficient becomes 3, and same with this coefficient here. Remember, everything that's related by oxidation and reduction has the same coefficient, or the same change in coefficient as we do this. We have to double the coefficients for HNO3, so we get a 2 there and a 2 there for NO, because those are tied together. Now we have to balance the rest by inspection. So we see that our zinc nitrate has 3 times 2, which is 6 NO3 minuses. So that means we need 6 more HNO3s to balance that. And then for water, this one's a little bit of a bear. So let's see, we have, on the reactant side, we have 2 times 3 is 6, plus 18 is 24 oxygens. On the product side, we have 6 times 3 is 18, plus 2 is 20, so we need 4 more waters. All right, so again, that one required a little bit of doing. I'm going to go through it quickly so we can move on, but we have 4 waters to balance. And then the final form of our equation would be 3 zincs, and then we can recombine these at the end. So 2 HNO3s that we needed to balance number of electrons, 6 more to supply the nitrate that we need for our counter ion here, so that's a total of 8 HNO3s. And then the product side, we have 3 zinc nitrates, 2 NOs, and 4 waters. All right, again, the 4 waters make sure that we have the same number of oxygens on both sides, which would be 24 in this case. All right, and same number of hydrogen as well, 4 times 2, 8 times 1, so 8 hydrogens on both sides. All right, so that's the last one I want to go through as an example. We'll see more on the review and on the test and on the homework and everywhere else, so try to get a lot of practice with these. Any last questions on balancing oxidation and reduction reactions? All right, let me see what we have left. Let's do this next time because it ties in better. I don't want to rush this. All right, so we'll table this till next time. So the last thing we're going to cover in Chapter 6 is going to be stoichiometry of solution reactions, which is a lot of review of what we've already talked about, a couple of new things that we'll throw in related to molarity, and we'll cover that Wednesday, and then we'll be all set for the test next week.